Okay, we have a definition for the definite integral of a function f from a to b. And as you can see here, we have some pretty fancy looking notation here, mathematical symbols here, and we need to understand what this all means. So I have a diagram here, an example of, we have f at x curve here, and I have the boundaries to the left, a, and the boundary to the right, B. Now, the area underneath this curve we've calculated before, and we're going to look at it a little bit differently here. We're going to divide this region from A to B into rectangles, um, and we're going to divide it into n number of rectangles. So that means if we were to determine the distance from A to B, which would just be B minus A, and divide it by the n number of rectangles, the widths of each individual rectangle we'll call delta x. And delta x will be calculated by B minus A divided by n. So this part here of the definition refers to the width of each rectangle, delta x. Now, we don't know how many rectangles there are, right? We can divide it into 4 as we did with Riemann sums, or 6, or we can do 100. So let's just call it n, right? So there's a partition here of the area below the curve into n number of rectangles. Each rectangle will have a delta x width, and the height will define using the right corner method. So the upper right corner of the rectangle will be the height of the rectangle, and that will be f at whatever x value is over here, right? So we know the area of a rectangle is just length times width, or in this case the height, f at the x value. So the ith rectangle will have the x value xi times the width, which is just delta x. So this would be the area of this rectangle here with this height. So we have that here in our definition. Okay, but we have this symbol here, sigma, and it ranges from I equal 1 to n, and we also have the limit here. So let me explain where that comes from. If we were to sum up all these areas here, all these rectangles, we would have f at x1 times delta x, and plus f at x2, right, x2 is here, times delta x, plus dot dot dot, and the last rectangle would be f at b, but instead of b, let me just put xn, so that would be the last rectangle, the nth rectangle, times delta x. Okay, so this is a sum. Now in mathematics, instead of writing this all out every time, we can use this symbol here, sigma notation of this. So we have a common delta x for each rectangle, and what's happening is x1, x2, x3, all the way up to xn, that's changing. So we'll write that as xi, where I starts at 1. So I starts at 1, and we'll go all the way up to n sequentially. So that's the sum of n rectangles. So that takes care of this part of the definition, the sigma. It's just a symbol for the sum. Now the limit as n goes to infinity. So we can continue to partition this and have as many rectangles as we want. What's the maximum number of rectangles we'll have? Well, we can do 1,000, 1,001, 1,002. We can do a million, 1,000,001. we can keep on going as high as we want. What happens is this delta x gets smaller and smaller and smaller. We have more and more rectangles. But each height of each rectangle will still be defined by f at x1, x2, just that we'll have more terms here. So if we take the limit of n going to infinity, we get um, a better and better approximation. In fact, when it goes to infinity, we'll get the exact area underneath the curve. So that explains this limit. So we have the exact area below the curve here. And what this is just another notation for that. The dx refers to this delta x here. F at x is just the f at xi part here. And this part here, the limit as n approaches infinity of this sigma, the sum of all these rectangles, we'll use this symbol here. It looks like an S. So it's a more compact notation, not as intimidating. And since this goes from A to B, we'll just put the lower limit here and the upper limit here, A to B. So that's what we define as our definite integral meaning there's boundaries here, a left limit here, A to the right, B. Okay, and what's this mean? I talked about that too. If you start at A, f at x1 will be just one delta x strip to the right, right? So just going right across here, a delta x. X2 would just be two delta x's away from A to the right. So that's what that means here. Okay, so I hope I clarified this, and there's your definition for the definite integral of f from A to B. Okay, so in the special case where we have f at x completely above the x-axis, positive, uh, this definite integral is the actual area underneath the graph from A to B. So let's just take an example. Say from 0 to 2 of the parabola x squared dx. What does this look like? Very quickly, we're looking at that, and then we're going from 0 to 2. We've calculated this before. It's just the antiderivative, so our f at x is the antiderivative, so 1/3 x cubed, and we calculate it by f at 2 subtract f at 0. And so it's 1/3 2 cubed minus 1/3 0 cubed, and we get 8/3. Okay, so this is in the special case where f at x is completely above the x-axis from 0 to 2, for example. But f at x can be any curve, and it can go below the axes. So we're going to look at that now. So the area under the graph is not necessarily the interpretation of this all the time, because f at x can be below the curve at times. So here's an example where f at x starts off above the x-axis, but then goes below the axis from 0 to 5, from 3 to 5, it's below. So let's look at this definite integral from 0 to 5. And f at x is 3x minus x squared dx. Okay, so the antiderivative, let's just do that here. We add 1 to the exponent and then divide, so that would be 3/2 x squared minus, add 1, we get 1/3 x cubed. So if we were to use this f at 5 minus f at 0. Let's see what happens here. Get 3 halves, 5 squared minus 1/3, 5 cubed. All that we have to subtract f at 0. So I'm running a space here. If you were to plug in 0 here, you'd get 0. So just have to work this out. 25/75 over 2 minus 125 over 3. And we get, need a common denominator here. So say 6. 3 times that, that's 225. And 2 times that is 250. And that's over 6. And we get what? Negative 25 over 6. And we get a negative number here. So what ended up happening here? Well, I'll tell you here, long story short, the A1 area is a positive number. This A2 ended up being a negative number, and then summing them together, you get a negative number here. So it turns out it's not the sum of these positive areas, because A2 ends up being negative. So it's really like a difference of areas. So there you have it. There's the definite integral and a couple examples how you can actually calculate it.